Well, hey, it's Dr. J. I'm back with some more of the graphing strategy. This is a quintic, or a fifth degree polynomial, that was originally intended to be part of the last lecture, but time ran out and I got a little long-winded on the last example, so we just bumped this forward. We'll do a couple more graphing examples, and then we'll transition into the primary objective today, which is the application in business called the point of diminishing returns. But before we can do that application, we need a few more examples of just graphing, because it'll be based on the concepts that we learned with the first and the second derivative to gain some important information about the graph. So without any further ado, let's get right into it. The strategy is to take the derivative, first derivative first, second derivative second, and find critical values and possible inflection values and go from there. So we just dive right into it. 5 times 0.2 is 1.0, x to the fourth. Or you could just say 1. 4 times 1.6 is 6.4, x to the third. 3 times 0.8 is 2.4, x to the second. This one's just a whole number, 16. So 2 times 16 is 32, or negative 32x. And then, of course, this is a linear term. So it's just 12.8. The derivative of negative 12.8x is just negative 12.8. And we all know the derivative of the last term, the constant, is 0. Now, because this is a fourth degree polynomial, so we started with a fifth degree and now we have a fourth degree. Finding the critical points is very difficult. So solving f prime of x equals 0 in this case is difficult. So what we're going to do is we're going to wait until we've found the inflection points. So what we'll do is we'll keep going. We'll kind of skip through the critical values. And we'll come back and solve this later after we have more information. One of the primary uses of the derivative is to reduce the power of a polynomial. So if you start with a fifth degree, you take its derivative, you get a fourth. Then you take the next derivative and you get the second, which would be a third degree polynomial. So second derivative will be 4. Now again, it's 4 times 1.0. So I could write 4.0 x to the third, or you could just write 4. This one, I think it's 19.2 x to the second, 3 times 6.4. But I should probably double check that. 6.4 times 3, yeah, 19.2. 2 times 2.4 is 4.8 x, and then minus 32. So that's our second derivative. Solving this is also hard. Without a hint. Yeah. Or a lot of time. If you had a lot of time, you could do some trial and error. It's not impossible. But I don't want you spending a lot of time. So I'm going to give you a hint. I'm going to say x equals negative 4 is an inflection point. So I'm going to give you one for free. Typically, I do that if the problem is beyond the reasonable amount of time that I would expect you to spend. I spent the time ahead of time solving it. I used a computer. But I do know how to do it by trial and error. And when I was your age, I did it the long way. But now I've got a computer that solves it for me. So I went ahead and found one ahead of time. tell you that this is already one solution, okay, to this equation. It's a critical value. So now I'm going to find the other two. All right, there are 3 total critical values. Typically, whatever the exponent is, it's not 100% guarantee, because we've seen some equations that, don't have as many critical values, or sorry, PIVs, I guess, possible inflection values. So what we're going to do is use synthetic division. So we've got 4.0, 19.2, 4.8, and negative 32. We take the one that we know, we put it out here in front, put a 0 here. You add, you're adding nothing, so it just comes down the same. You multiply. Now you see why I put the 0.0 part, because it helps with the decimals, helps you line them up. Then you add. Then you multiply. I think it's 12.8 negative. Then you add. You get 8, negative 8. Technically, it's 8.0. Then you multiply, you get 32, and the remainder is 0. Now, that tells us that it's an inflection point. In other words, f double prime of negative 4 is equal to 0. That's what this last box tells you. So this is called synthetic division. If you've seen it in pre-calculus or in algebra, it's done in various different levels: intermediate, advanced, college. So if you haven't seen it, this is the second time we've seen it. It's used if you already know a value that gives you a solution. You can use that value to reduce the equation and make it easier to solve. So now this equation is much easier to solve. It reduces the power, so I get 4.0x squared plus 3.2x minus 8.0. So this is the simplified version of the derivative. So let me just copy this thing down up here. Just copying it down. And then now I'm going to take this and bring it up here. So basically what I have is I have x plus 4. It's the opposite of negative 4. It's positive 4. You see why? I'm just going to stop for a minute. If you plug negative 4 into this, that would become 0. So that's this factor here, the factor that's equal to 0. And then you have the rest of the factors, 4.0x to the second plus 3.2x minus 8.0. So if you had a lot of time, trial and error, you could have gotten from this step to this step without using calculus, just by using algebra and trying lots of different possibilities. It's not easy, but it's not impossible. So I give you a hint, and then that gets you to this step a lot easier. All right. Now remember, our goal is to set this equal to 0. So we're setting this equal to 0 and solving this. All right, take a good look at that, because I got to erase all this. Yeah, without the hint, this video would probably be an hour long, and we would only get through one example. So the hint's very important. All right, so now let's keep going. Let's try to solve this. I don't know. Let's just use the quadratic formula. So we're setting this equal to 0. You could multiply everybody by 10 if you like. You think that'll help? I don't know if it will. You're going to get 40x squared plus 32x minus 80. What else could you do? You could divide everybody by 4. Do whatever you want to do to try to make the problem a little easier to solve. Oh, actually, you could go bigger than that. You could do 8. You see how they're all still divisible by 2? So I could divide them all by 2 now. If I would have noticed that, I could have just done 8. That would have been easier. So now I get 5x squared plus 4x minus 10. All right, so give this a minute and see if you can solve it. If you can't solve it, then just use the quadratic formula. So just give it a minute. I like to sing the Jeopardy song. Does that work? Nope. 5 times 2 is 10. 5x times x is 5x squared. Unfortunately, the middle term won't come out to be 4. So I don't think it's possible. So let's go ahead and the minute is up. The Jeopardy theme has expired. Let's go ahead and use the quadratic formula. So x is negative 4 plus or minus the square root of 4 squared minus 4 times 5 times negative 10 all over 2 times 5. There's your formula. Now, you know what? I spent a few minutes doing this. I could have just done it from this, right? I could have taken 4.0 and 3.2 and 8.0 and plugged them into here, and I would have got the same result. All right. Let's see what happens. Negative 4 plus or minus the square root of 16 plus, what's that, 200 over 10. So 216 square root, 14.7. 7. I'm going to do 6.9, and I'll round it later. It's actually 14.696938, blah, blah, blah. It's always better to do a couple extra decimals and then adjust it later if necessary. So I've got x is negative 4 plus 14.6969. So divided by 10. So 1.06, so 1.1, or the other one is 14.6969. So negative will be negative 18.69. So I'm adding the two negatives. Right. I've already done the positive one, which is 1.1. Now I'm doing the negative one, and then divided by 10. Negative 1.9. negative 1.86 or negative 1.9. All right. So those are our PIVs. Oh, and then we have this one as well. This one's actually very easy. X equals negative 4. That was already given in the hint. Right. I just rewrote it as x plus 4 so that everybody would see that when you are factoring, you know, it's x plus 4. When you're solving, it becomes x equals negative 4. I think that's obvious from algebra, but I never know. I always figure I'll err on the side of caution when it comes to that. So those are our 3 PIVs. So let's list those over here. PIVs. So far, they're just possible inflection values. I don't know if they're actual inflection points yet. So I've got negative 4, 1.1. I might as well put them in order. Negative 4, negative 1.9, and 1.1. All right. I won't know until I test them. So this is the reason why I wrote it this way, is because I can use this as my derivative test. Use this for my derivative test. I'm going to put the 4.0 out in the front. Then I'm going to put x plus 4. Then I'm going to put x plus 1.9. And then x minus 1.1. So this is what's called the factored form of the derivative, of the second derivative. It's much easier to do the test, what's called the sign test or the second derivative test. It's much easier to use this version. But you could also use this version, or you could use the original version. It's really up to you. So I've got 3 critical, or 3 partitions. So I've got negative 4, negative 1.9, and 1.1. All right, so let's test a number over here. Say negative 5, something in here, negative 2, or negative 3 would work as well. Something in here, how about 0? I always love 0. Then something over here like 2. And don't really spend a lot of time with the calculation, right? This is a sign test. All you care about is plus or minus. So plug in 2. That's going to be plus, 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 plus. Everybody will be plus. Plug in 0. This will be minus, plus, plus, plus. So that'll be minus. Right? 1 minus and 3 pluses. Notice the 4.0 does count, but it always counts as being plus. So if you forgot the 4.0, it wouldn't affect your answers. Right? Now, there might be some problems where this leading term is negative, and then it would actually affect your answers. So I'm just showing you that that number is part of the game. It just doesn't always, affect the outcome of the game. All right, negative 2. So that one will be negative, negative, positive, positive. So 2 negatives and 2 positives. That's positive. You could probably guess this last one's negative. You shouldn't, though. You should actually do it because sometimes it changes. So negative 5. That one will be negative. That one will be negative. That one will be negative. That one will be positive. So you'd have 1, 2, 3 negatives and a positive. So it's negative. So our concavity is down, up, down, and up. Okay. Let's write that over here. Oh, by the way, these are no longer possible inflections. These are now inflections. All of them are changing signs. So we have 3 inflection points or 3 inflection values. I'm not going to ask for the y value yet. I might need it at some point, but I'm not going to ask for it yet. All right, so we got concave down from negative infinity to -4 union union -1.9 to 1.1. We have concave up. Everything else from -4 to -1.9. Union 1.1 to infinity. All right, now we've been waiting on this one. So sometimes one of these inflection values, so now we're coming back to this, check if an inflection value is also a critical value. Sometimes you get an inflection value that's also critical. Right? You get sort of a double dipper. Yeah, we saw that in the last one. If that doesn't happen, then the problem is cruel and unusual, and I probably wouldn't be giving it to you. So I'm always going to sort of give you a little, especially with these larger ones, right? With a larger degree polynomial, I got to give you something to crack it open. So let's see. And let's go for the most, nicest one, -4. I don't know. I don't know if it's going to work. I sure hope it works. Because if it doesn't, then I have to try one of these decimals. And I really don't want to have to use decimals. But I will if I have to. Don't make me. So 1.0, 6.4, 2.4. So now remember, we're doing the first derivative now. This was on hold. We're coming back to it. All right, so we're hoping that this is 0. I don't know. If it is, then that means we got another one, right? All right, so let's see. We get 1. We get -4.0. We get 2.4. What's that going to be? 9.6 negative? Yeah. 4 times 2.4. I don't even have to guess on that. Oh, no. 4 times 2.4. Yeah, 9.6. And then I'm going to add 2.4. So I get -7.2. And I'm going to multiply 7.2 times 4, 28.8. Double check the sign. A negative times a negative, so that's positive 28.8. And then plus -32. It's -3.2. It's looking pretty good. Negative times a negative. Positive 12.8. And winner, winner, chicken dinner. Yeah, we got it. Yeah, and you will get it too. I'll give you one. Yeah. All right. So now what I have f prime of x is x plus 4. All right. Remember, if a -4 is a critical value, well, then the factor is x plus 4. And then I have x squared, or 1.0 x squared. You want me to just write it all out so it looks clean? It's really just 1, though. Plus 2.4x Oh, actually, it's not squared. It's cubed. X squared minus 7.2x minus 3.2. And we're going to need another hint. I got to keep giving you hints. All right. F prime of 2 is equal to 0. So I'm going to give you another hint. So I've got 1.0, 2.4, negative 7.2, and negative 3.2. I considered not doing this problem, but it was so much work on the back end to create it and to get the graph right that I figured, why, we might as well do it. We might as well stick together on this one. All right, so we get 1 times 2 is 2. 2.4 plus 2 is 4.4. 2 times 4.4. Oh. Doesn't seem to be working. Something went wrong. I didn't get 0. 1, 2, 7, 3. Well, maybe. Maybe I'm panicking for no reason. 4.4 times 2, 8.8. Oh, no, it's fine. I was panicking for nothing. Add those. So 7.2. I was being skeptical that it wasn't going to work, but it is. 2 times 1.6 is 3.2. Whew. Oh, man, I was sweating there for a second. I got to here and I thought I wasn't going to get 0. So before I, looked silly, I wanted to pause and just think about it for a minute, but everything worked out okay. Yeah. So I will be giving you a couple hints on this type of a problem, mainly because the degree is so large. Anything bigger than like 3rd degree, I have to give you some hints to help you crack it open, or give you some software, computer software, which you probably have access to, but I'm doing it in a very pure sense, which is, use the lecture, use the hints, and see if you can crack it open that way. All right, we got it. So we have now 4 critical values, right? Because look, their degree is 4. So f prime of x is x plus 4, x minus 2, right? Because 2 worked. And then we have this polynomial. That's going to be 1.0 x squared plus 4.4x plus 1.6. Now, that's a small enough polynomial that I don't have to give you a hint. You should be able to solve it yourself. So these 2 have already been solved. Thanks to the hints. This one you can solve now. I'll do it with you. It's 1x squared. I'm not going to write it. It's a 1. Plus 4.4x plus 1.6 equals 0. All right. If you want to multiply everybody by 10, you can. I'm not going to. It doesn't really make it any easier. I'm also not going to waste your time with the 2-minute rule. I'm just going to plug it into the quadratic formula and just get it over with. So there's the quadratic formula. So we've got negative 4.4 plus or minus 19.36 minus 6.4. 19.36 minus 6.4, 12.96. I'm just going to change that on the whiteboard. All over 2. So the square root of 12.96. Oh, wow, that's kind of cool. It's exactly 3.6. You know what that means when that happens? It means that I was a little bit too impatient. I could have actually factored that. I don't know how good you are at factoring with decimals. I'm actually not very good at it. I'm pretty good at it with whole numbers, negative integers and things. You know, I've been doing it for years. I can sometimes get away with some basic fractions, even at my age, you know. But with decimals, factoring is typically not easy. But calculators love decimals, right? That's what calculators were made for. So, all right, so this is going to be our two critical values. We've got one of them is negative -4. The other one is -4.4 plus 3.6 divided by 2, -0.4. So I went ahead and just put all this into the calculator, and I got two different numbers. Remember the plus or minus. Now notice they both came out to be negative, because when you do the plus or minus, the 3.6 is not big enough to bump one of them over onto the positive side. So both of these answers stayed on the negative side of the line, of the axes or whatever. So notice now my f prime of x has gotten very, very simple. So what the quadratic formula gives you is it gives you these additional factors. Yeah. So it's going to be x plus 4 again, right? Another copy of x plus 4, and then x plus 0.4. And typically when that happens, the factor that appears twice, we write it like this. That was a lot of work. You really, I mean, we're already 30 minutes into the lecture and I'm still only on example 1. Which now you know why I didn't try to squeeze this one into the last lecture. Because, I mean, you'd probably still be watching the last lecture if that were the case. All right, well, I hope everybody realizes what we just went through. We went from the original function to the first derivative. Then we put the first derivative on hold. I already completed the second derivative. That was actually the easier part. And I wrote everything down. All of this on my little sidebar here all came from the second derivative, which I've already erased, right? That was the easy part. Then I went back to the first derivative using what I knew from the first derivative, and I continued to break it down. So now I've got my first derivative, and now I'm ready to test. So my CVs, my critical values are -4. Right? Now, even though that one occurs twice, you don't have to type it in twice. Just type it in once. What else? +2 and -0.4. Just for fun, let's put them in order. You don't have to, but I like to. Because I'm going to do the sign test. And on the sign test, they do have to be in order. So you might as well put them in order to start with, and that'll save you some work. All right, and again, sign tests should go rather quickly, right? All of your energy is in finding these numbers. Once you have them, the sign test should be pretty quick. So let's test 3, 0, -1, and -5. Remember, you get to pick your own numbers as long as they actually lie in that bin or in that partition region. That's fine. All right, just pick any numbers you like. If you don't like my numbers, try different numbers. One thing you can do to challenge me is, if I pick 3, you can pick 4 and see if you still get the same thing. You will, because it's a fact. So it doesn't matter what number you pick in that region. All right, now again, you can use the original to test. You can use this one to test, or you can use this one, or you can use this one. All right, you can test any of these that you like. They are all different ways of saying the same function. I'm going to use the last one. That's definitely the easiest one. All right, but all of these are the derivative. So, all right, so let's get on with it. Let's start with 3. So 3 plus 0.4, that's positive. 3 minus 2, that's positive. 3 plus 4, that's positive. You're squaring it. It's still positive. Everybody's positive. Right. If you want to take a guess, you can guess this. Yeah. Once you know one of them, you can guess the other ones. I don't recommend that, because if you do that and you're wrong, you won't know it until it's too late. So if you want to write this down as a guess, go ahead. And let's go ahead and continue the test and see if you were right. All right, let's test 0. 0 plus 4, that's positive. 0 minus 2, that's negative. 0 plus 4, that's positive. When you square it, it's positive. So you have a positive, a negative, and a positive squared, which is going to be negative, right? Because this negative in the middle makes the whole thing negative. All right, let's try -1. -1 plus 0.4. That's negative. -1 minus 2. That's negative. So far you got 2 negatives. -1 plus 4 is positive 3 squared is positive. Positive 3 squared is 9. It's positive. So this is positive. That's negative. That's negative. So 2 negatives, 1 positive. So that's positive. Let's try -5 now. -5 plus 0.4. That's negative. -5 minus 2. That's also negative. -5 plus 4. Well, that's negative. Yeah. -5 plus 4 is negative. But you're squaring it. So it becomes positive. So this is always positive, this one, because you have a square. That first factor is always positive. So you have a positive and then a negative and a negative. Ah, I'm glad I didn't guess. That is the reason why you should never guess. All right. Or if you guess, that's okay, but you're not going to be right 100% of the time. There's that 1 in 10 chance, probably. In this case, it's probably like 1 in 4 that you're wrong. All right. So I would have been wrong had I stuck with my guess. Anything can happen. Any possibility. Any combination of positives and negatives is possible. Right? The most likely is that they alternate, plus, minus, plus, minus, plus, minus. So if you're a gambler, that's what you would gamble on. But, you can lose. Right? That's why it's called gambling. So we have increasing, decreasing, increasing. And now we're ready to graph. Finally, after all that work, we are ready to graph. What do I erase? I can erase all this now. So we have let's see, this is increasing. So we have increasing from -infinity to -4, and then from -4 to -0.4. So we just scoot right past that. This is all increasing, and we stop at -0.4. And then it's increasing again from 2 to infinity. It's decreasing only in one region from -0.4 to 2. We have a local max of blank. All right, let's see, where's the max? The max is where it goes from increasing to decreasing. This is a max. Yeah, it's concave down. Yeah. I already erased my second derivative, but if I would have plugged this number into my second derivative, I would have gotten a negative number, which means it's concave down. Or you could just use the first derivative test. It tells you the same thing. It's going from up to down, so that's a max. This one's going from down to up, so this one's a min. All right. So we're ready to start graphing. I do need to find these values very quickly. All right, so let's adjust the screen a little bit and try to get all this information in here. The last thing we need to do is figure out the y values. So this one is sometimes called y max. Let's see right here, y max. I don't know what it is yet. And this one's y min. Let's say a local max of, that's the y value. So that's the only time that you need to use the original function is to determine the y values. I'm not asking for the y values of the inflection points. I might need them at some point. Right now I just have the x coordinates of the inflection points, or the inflection values. You can call them either one. So all of this over here was done with the second derivative. And all of this was determined with the first derivative. But now we have to go to this function and actually calculate the y values. So let's do y max. So we'll plug in -0.4 into here, and I'll do some scratch work to try to keep moving here. So we got a 0.4, -0.4 to the 5th power. Tiny negative decimal, and then multiply that by 0.2. And again, if you have a fancier calculator or a device that will do this, some of them will allow you to plug in type in this entire expression, then just put the number in one time. I don't have one of those. I'm just using a phone. I do have a traditional scientific over here that I'm not going to use because I already have this one going. So -0.4 to the 4th power, which really didn't matter that it was negative. It's going to come out positive. And then times 1.6. So that's plus point here. I'll stack them up. 04096. This is sometimes called the bookkeeping method, like you're an accountant and just stack everything all up. Let's do -0.4 to the 3rd power. And then times 0.8. It's like debits and credits. Debits and credits. -0.4 to the 2nd power. Again, for the even powers, it doesn't really matter that it's negative. And then times -16. I guess that matters. It matters that the 16 is negative. 2.56. -0.4 times -12.8. 5.12. I want to double check that one. 0.4 times 12.8. My calculator acted funny. No, that's right. 5.12. And then the last one, there's no x, so just plus 31.2. So go ahead and do all those on your calculator. 31.2 plus 5.12. I'm going to do all the pluses first. Plus 0.04096. So that's all the sums. And then we'll subtract all the negatives here. So 2.56. Subtract 0.0512. And that's interesting. I don't know if it means anything, but it's certainly interesting. Minus 0.002048. And I'm just going to round to one decimal place, or the 10th, the 33.7. That'll be my max. We call it a local max. You'll see why in the graph. It could possibly be the highest point on the graph, but the general term is it's locally the highest point on the graph. We'll get to that later, whether it is the absolute highest. There's a whole separate section devoted to that. But for now, we use the term local. So the derivative tells us that at least, nearby in that general vicinity, that is the highest point. It's like a little peak, top of the mountain. Might not be the highest mountain in the whole world, but it's the highest mountain in that general, what we call a neighborhood. All right, so that was for the decimal. Now, for x equals 2, I'm going to find the local min. It's going to be a little bit easier because powers of 2 you could do in your head. Now, I would probably multiply the decimals with the calculator, but let's do the powers of 2 in our head. So 2 to the 5th power, it's a nice mental exercise. 2 times 2 times 2 times 2 times 2, 5 2s. That's 32. Yeah. And then now you just do that part very quickly and then multiply it by the decimal. So 6.4. So 2 times 2 times 2 times 2, that's 16. And then times 1.6. That's 25.6. 2 times 2 times 2, that's 8. Times 0.8. That's 6.4. Two times 2, that's 4. And then times negative 16. Be negative 64. 12.8 times 2. It's actually negative 12.8 times 2. So negative 25.6. And then I have the positive 31.2. So let's do the positives first. 31.2. Let's do all these positives first. Or you can do the negatives first. It's up to you. So 6.4 plus 25.6 plus 6.4. Oh, I should have just canceled the 25.6s, but whatever. I'm already done. So I did all the positives. Now let's, oh no, I didn't do 31.2 plus 31.2. All right, so 69.6 is all the positives. Now I'm going to subtract the negatives, which I probably could have just canceled these guys out, but I'm already halfway there, so I'm just going to keep going. 25.6, so now I'm down to 44, and then minus 64. Oh, look at that. Very nice. Negative 20 is the minimum. All right. So we're almost ready to start graphing. We are going to need some inflection values. Because this is already taken a very long time, I'm going to, let's write this down up here. So y max is 33.7, x is negative 0.4. Some of it might be slightly off screen, but it's all stuff that we've calculated in this video, so you have it written down somewhere. Negative 20, x is 2. All right, let's see if we can get all of this on a nice graph. And I might need to plug in a couple of these inflection values, or I could just tell you that I've done it off screen and I can just tell you what the numbers are. And then you can check my math and send me an email if I get if the number you see on the graph today is not what you think it should be, but we'll see how time goes. All right, so let's do the So let's do the max and min first. Oh, we should probably scale this out. So this will be 1, 2, 3, 4. -1, -2, -3, so on and so forth. Let's do 10, 20, 30, 40. -10, -20, etc., etc. All right. So at -0.4, which is going to be right about here. I'm not being very precise. It's very close to a half. It's going to be 33.7, so right about here. Just a little bit shy of 35. 33.7. Okay, and again, this is just a sketch, so it doesn't have to be perfect. And then at 2, it's -20. Well, that one's easy because I got -20 on here, so 2 and -20. So that's my max, that's my local max, that's my local min, which means that I kind of know the graph is going to be kind of shaped like this: concave up for a min and concave down for a max. So I'm already starting to piece together the graph. Okay. Now, let's do the inflection points. All right. I'll go ahead and give you one that I already did in advance. If you plug in -4 to the original function, just to save us some time, I already did it. You get -20 again. It's the same as what you get when you plug in 2. It's kind of a coincidence. It's not really, there's no real like magic there or anything like that. So this is one of your inflection points. Say I, P, or sometimes I call them inflection values. Since I know the y coordinate is -20, or you know it because I did it in advance, this is telling me that it's changing its concavity here. Yeah. Now you might remember this was one of the critical values that turned out not to be a max or a min. So what that means is it's looking like this. It has this little S shape. It turns like it wants to be a max, or perhaps it wants to be a min, and then it changes its mind at the last second. It's having an inflection at that. It's having an inflection moment. All right. All right. And then I'm going to go ahead and tell you the other two as well, because I can already tell we're not going to have time to calculate them. You can check my math. This is going to be approximately 10, and these are also very similar values. They're both approximately 10. So if I were to take these inflection values and plug them back into the original function, they both would come out to be very close to 10. So right here at -1, you have an inflection value or an inflection point. We have LM, or let's say L max. I'm just going to say max. Down here you have a min. All right, and then you got another inflection point right about here. So this is 1.9, and then this is negative 1.1. Again, these are just rough sketches. They don't have to be perfect. Yeah, just right about there, and then there's 1.9. I always say they don't have to be perfect, and then I spend a bunch of time trying to make it perfect. So, so what do we got going on here? We got concave down, right? Concave down, negative infinity to negative 4. So like this. That's concave down. Then it's concave up from negative 4 to negative 1.9. Oh, shoot. I got these backwards. I'm glad I caught that. Negative 1.9 is right about there. And then 1.1 is going to be right about there. There's a lot of symmetry in this graph where points are very close to the same value. These ones are actually approximations. Again, you'll have to check. So I'm going to say DIY to check that these are right. Who knows? They might come out to be exactly 10. I'm sort of just estimating it based on my experience. So then this is now concave up until you get to negative 1.9. So that's how important the concavity is. It tells you kind of how to draw the shape. Then it goes concave down again until it reaches the max. Then it continues concave down till it reaches the next inflection point. So this is the peak or the hump, the camel's hump, so to speak, or the mountaintop. Then it goes concave up again, at 1.1, and then it's concave up all the way to infinity. And so this is the U-shaped graph all the way to infinity. And there you go. That is a quintic polynomial with full calculus analysis, first, second derivative, and the graph. And so I hope that was informative. It's a very long process. So if something like this were to occur on a test, there's two things that I would do. I wouldn't put this particular problem on a test, but I could put something in this family of functions. I would probably give more hints, or at least as many as I did, and I'd probably make the numbers a little bit easier so that they calculate quicker, because the process is pretty straightforward, but it gets the nitty-gritty gets time consuming. So basically, I just want you to know how to find the derivatives, first and second, perform the tests, determine the important answers to the questions, and then draw or select an appropriate graph. Okay. Well, this is going to be a very short lecture or a very long lecture with a very short amount of content. We're only going to have time for one more today. And the business examples are going to have to wait for another day. So let's wrap this up with a function you've already seen in a previous video, but we did not draw the graph. We only had time to analyze the characteristics of the derivative, but without actually drawing the graph. And I might have mentioned at the time that I would come back to this function. Now, it's been a while since we did this, not a week maybe. So I'm going to start off with a new function in the same category. So we did one very similar to this, 2x squared plus 10x plus 14 over x squared plus 5x minus 24. So when I say that we've done this problem before, I mean we've done a problem of this type. Call this a rational function. It's a polynomial divided by a polynomial. Okay, and the numbers might be different, but the general flavor of the equation should remain the same. Okay, so this is our function. Quick review of what partition numbers are, or partition values, same thing. Partition numbers are x values where f of x does not exist, or f prime of x is equal to 0. We call those partition numbers. So that's going to partition our x-axis into various regions. I should also mention that if f of x does not exist, that also means that f prime would not exist also. But we won't bother with that, because if the function itself doesn't exist at that point, well, how could a derivative exist if the function doesn't exist at that point? You can't take a derivative at a point that's non-existent. So that's more of a Captain Obvious statement here. Although I don't know how obvious it is all the time. So remember, in order for a function to not exist, we set the denominator to be equal to 0. And we solve for x. That's going to be the easiest part of this entire problem. X squared plus 5x minus 24. I usually make these factorable, or I try to make them factorable. I'm not always successful. Sometimes you have to use the quadratic formula, but in this one it is. We have 8 and 3, 24. Positive 8, negative 3 will give you a middle term of 5. So you set these equal to 0, and you get x equals 3 and x equals negative 8. I don't need to show you the math. You all know if a factor is a plus, then a solution is a minus, and vice versa. If the factor is minus, the solution is plus. So those are our first two partition numbers. Our next two partition numbers come from the derivative. Now this is going to take lots of steps. It's very messy. So hold on to your hat or your pen. Be prepared to pause very often if necessary. So what I'm going to do is I'm going to write down these partition numbers, the two that we got easily, and then I'm going to save room for this messy calculation. So what do we got? We got, so we're going to save me x is equal to negative 8, 3, and I don't know, we have more to come. We're going to have to find a derivative of f. I guess I could have done that first, but I just decided to do the easy thing first. Sometimes these problems are so easy that you can actually tell what these two numbers are without doing any math. I mean, you could do that. You could just look at the problem and immediately identify these two, and then you can get right into the business of taking the derivatives. All right, this is a quotient rule. So remember, derivative of the top. So that's 4x plus 10 times the bottom, x squared plus 5x minus 24. Minus the derivative of the bottom, 2x plus 5 times the top, 2x squared plus 10x plus 14, all over the denominator squared. The messiest part of this is the numerator. And in some of my previous videos, you stopped right now, right? And I think in the last chapter test, it said, don't waste a bunch of time, just type it in just like that, all right? But I said at the time, someday we're going to have to clean up this mess, right? And that day is today. So today's the day that we have to clean up this mess. So let's go ahead and do it. It's not that bad. It just wasn't necessary until now. And so now we're going to finally do it. So we got 4x times x squared. That's 4x cubed. 4x times 5x. That's 20x. 4x times negative 24. That's 96, negative 96x. We've got 10 times x squared. That's 10x squared. Notice where I write it. I almost forgot my square there. So those are squares. I write them underneath. 10 times 5 is 50x. And 10 times negative 24 is negative 240. Now for this one, it's a little bit tricky. So watch what I do. I first distribute the negative. So I make that negative 2x and negative 5. Right? I'm just trying to save some board space here. I mean, I could have, wrote out a whole another step of that, but just there's a negative out here. So I first distribute it. And now when I do my distribution lines here, remember this negative is going with that 2. So that's going to be negative 4x cubed, negative 20x squared, negative 28x, right? And then this one as well, negative 10x squared, negative 50x, negative 70. Now this is my favorite part. Oh, and don't forget about the bottom. Although it really doesn't matter right now, it does matter in the long run. So let's have some fun. 4x cubed, negative 4x cubed. 20x squared, negative 20x squared. 10x, negative 10, or 10x squared, negative 10x squared. 50x, negative 50x. No. So the only terms that survive are negative 96, negative 28. I'm a little tired, so I'm going to use my calculator. Those are both negative, and I'm adding them, so that's going to be negative 124x. And then I've got these ones as well, 240 and 70, which are also both negative, so that's negative 310. Everything looked good. All right, that looks good. And then the bottom is x squared plus 5x minus 24 squared. All right, so remember, we're looking for partition numbers still. This is just to lay the partition down. So we're going to set f prime of x equal to 0. And for that, you only need to look at the numerator. Remember, the denominator has already been taken care of. Right? In fact, the denominator technically is not allowed to be 0. It's an excluded value, and I'll explain more about that later. When you're solving, you only solve the numerator. Okay. Just double checking all my signs. Everything looks good. Everything looks good. If there's a mistake, you want to find it now. So we're going to add 310 to both sides. You could probably do this part with mental math. And then divide by negative 124. So 310 divided by 124 is 2.5. Negative 2.5. All right. They don't really have to be in order, but you know what? I like them in order. It just makes so much nicer for the long run to have them in order. You're going to be graphing it eventually anyway, so there you go. So that's your last partition number, negative 2.5. It joins the group. So that's a lot of work. So the hardest part is over. That's finding those partition numbers. I'm going to need this derivative later. So I'm just going to save it over here. And we'll move on to the next step. So we'll save me f prime of x. I mean, I could just write it on a piece of paper, not use my board space, but I might forget if it's not just right here in front of me. So, all right, I can erase all this stuff. Well, that was a heck of a lot easier than solving the last example, right? These ones look scary if you don't know what you're doing, but they usually solve out pretty nicely. Okay. So we've got our partition numbers. Now remember, partition numbers are a larger collection than the critical values. The critical values are only the f prime of x equals 0 value. So we only have one critical value. All right, so now we're going to do our test. This is the first derivative test. Now, put the numbers in order. And then if it's a critical value, I usually use a solid partition. If it's a partition number that's not critical, that's called an asymptote. Vertical asymptote. So these are dotted lines on the graph in which the points do not exist. They're kind of like holes. Yeah, back when we were learning our limits and we were taking limits from the left and limits from the right, these are two-dimensional representations of that. It's, it's a point in which there is no x value. In fact, there's no y value either. It's like a point of non-existence. All right, y'all remember how the sign test works, right? I don't know. Do you? I can't hear you. Sure you do, right? You plug in a number, any number you like, and then all you care about is whether it's positive or negative. So I'm going to go in this region. So a number bigger than 3, say 4. In this region here, anything between negative 2.5 and 3. So how about 0? Yeah, negative 2.5 and 3, 0. Good. Anything between negative 8 and negative 2.5. I don't know, negative 5. You get to pick any number you like, as long as it's true. It has to actually be in that region. And then a number over here, say negative 9. All righty. Let's start plugging in numbers and see what happens. Let's start with, now remember, this is what we're testing. Testing the derivative. Now let me point something out. Because the denominator is squared, that means that the bottom is always positive. The denominator is always positive. So no matter what happens, I'm going to be doing the numerator divided by a positive number in all of these regions. In fact, I can save myself a lot of time by not even plugging in the denominator because I know it's going to always be positive. All right, let's do it. Plug negative 9 in here. Now, you do only care about the sign, so if you're not sure, use a calculator. But let's see if we can get away without that. Negative 9 times negative 124. That's like 1,000. Yeah, it's over 1,000. Right? Positive, right? Because negative times negative. And then you're subtracting 310. Well, if you have a number that's more than 1,000 and you subtract 310, it's still going to be positive. Okay? Negative 5. Plug it into there. Negative 124 times negative 5. That's going to be like, what, about 600? And again, if you're not sure, when in doubt, calculate it out, right? But it's still going to be positive, right? because it's a negative times a negative, and then you're not subtracting enough to bring it down below 0. Okay. Now over here, these guys are going to be negative. You plug in 0, right? Negative 124 times 0 is 0. And then you subtract 310. That's negative. Right? And then the same thing here. Negative 124 times 4. It's like negative 500 or negative 4 something. I don't care what it is. It's negative. And then I'm subtracting 310, so it's still negative. Now this is the first derivative test. So this tells me that there is a max at x equals negative 2.5. It is changing from increasing to decreasing. It's also increasing over here too, but that one's not changing. And it's also decreasing over here, but again, it's not changing. So only the one that's changing from positive to negative, that becomes your max. Right? Increasing, decreasing, that's a max. We will be able to confirm that with the second derivative, but I mean, if you make a mistake now, you'll catch it later when we get to the second derivative test. So we have a max, let's call this a local max. We don't know what y max is yet. We might need to come back and figure it out later. Okay, now we have increasing interval, negative infinity to negative 8. Now, this is why it's important to identify that with a dotted line. If it's a dotted line, you must use the union. Right? Now, you saw another example earlier where this was a solid line. If it goes positive, positive, or negative, negative, and it's a solid line, it means that it's a critical value. It's not a asymptote. Then you don't have to use the union. You could just say negative infinity all the way to negative 2.5. But the union is required. I like to think of it as jumping over the asymptote to get to the other side. You can't get across an asymptote without a union. And then decreasing on the interval negative 2.5 to 3. Now you got to jump over the asymptote and then 3 to infinity. So that's our first derivative information. Oh, I almost erased what I had said I wanted to save. So there's my first derivative. Don't erase it yet. We're going to need it. Now we're going to do second derivative. Second derivative. All right. It's kind of messy here. Let me get rid of some of this messiness. There we go. Okay, second derivative. Derivative of the top. Derivative of the numerator. Negative 124. That's pretty easy. Times the denominator. X squared plus 5x minus 24 squared. The whole thing, including the square. Minus the derivative of the numerator. That one's tricky. You got to do the 2 first. The 2 comes down. Then you ignore all of this. X squared plus 5x minus 24. All right, that's the chain rule. Then the derivative of x squared plus 5x minus 24, which is 2x plus 5. Then times the entire numerator, 124x minus 310. All right. All over the denominator squared. Now, since the denominator is already squared, you could write squared squared, but that would be silly. Squared squared is just 4th power. There we go. That's the squared squared. All right, now we are going to want to test this thing. So again, you know, in the previous homework, you were able to leave your answer in this sort of messy, unsimplified form. Let's try to clean it up a little bit. The first thing we can do is we can cancel one of these guys, that guy, and one of those guys. So we have common factors here that we can cancel. The next thing we can do is distribute. So we're going to get negative 124x squared minus, oh God, my brain's tired. Is that 720x? 124 times 5? 620. Let me double check that. 124 times 5. 620. Glad I didn't go with my guess. And then plus 124 times 24. 2,976. Oh, I need to save this, but let's see if I can get it work around it for now. Shoot, what should I do? I got this -2 and I've got a 2. So why don't we just combine those now? That'll be -4x. And then a -2 and a 5 is -10. And then I could do my distribution from this guy. It's not the cleanest, but I'm running out of space. So I've got positive 124 times 4. That's 496x squared. I've got positive 310 times 4. That's 1240x. This one I can do in my head because it's a multiple of 10. That's going to be 1,240x. 10 times 124. Negative times negative. Let me squeeze in the last term here. Positive 3,100. And all of this is over x squared plus 5x minus 24. It's now cubed because I've reduced it. Now, if I've done this correctly, which at this point it better be right, or we're going to be in big trouble. We have a lot of time we've wasted. So much time we've wasted. Let's see. 496 minus 124. 372x squared. All right, what else we got? Oh, that's interesting. 1240, 1240, so that's 2480. Yeah. And then minus 620. So that's 1860x. So those guys are all gone. And then 3,100 and 2,976. 6,076. So that, my friends, is your second derivative. Now, what do we do with it? Set it equal to 0. Yeah, set it equal to 0. I can hear you out there. And you're only going to have to worry about the numerator. Okay. However, when we go to do the sign testing, the denominator is cubed, which means it's not always going to be positive. Only squareds and fourths and even powers will always be positive. This is cubed, which kind of sucks for the second derivative. It means we're going to have to test it. We're going to have to test it. All right, so let's go ahead and set the Second derivative equal to 0. Just set the numerator equal to 0. So 372x squared plus 1860x plus 6076 equals 0. Oh, man, this sucks. Let's just see what happens if we use the quadratic formula. These numbers are so big, I don't want to have to try to factor numbers that big. I was about to spend 10 minutes trying to simplify this to see if they're all divisible by the same number. If it was obvious, you know, like they're all divisible by 5 or 10 or something, I probably would have done that. I guess it's 2. 2 is pretty obvious, but that's not really going to help very much. The amount of time it would take me to do that, I could just do this. So 1860 squared is 3,459,600 minus, now watch this, 4 times 372 times 6,076. 9,041,088. All of these numbers are positive, so you're not like worrying about double negatives. The negative comes with the quadratic formula. Remember, it's b squared minus, and then this is your 4ac. I just did it all in the calculator. I can stop right now. I don't even have to do the bottom, although I will just for good measure. It's a 744, right? The inside of this is negative. Stop. DNE. Yeah. So that means there are no inflection points. So I'm super happy because if this was not DNE, then I would have so much more work to do. I have so much more work to do and it would suck. Yeah. Especially at this point in the video that's gone on probably an hour and a half by now. All right. I'm almost done. I'm ready to draw the graph. Now I do have to mention for the second derivative, you have to use the partition numbers. Okay. So this is the second derivative test. What were they? -8 and 3. Yeah, because these are points where f double prime of x does not exist, right? Because you're dividing by 0. All right, but because we got no inflection point, there's no solid lines in the partition. They're both dotted. Yeah. Now, what's interesting is you can use -2.5 as a test number. It's not part of the partition. It was part of the partition in the first derivative, but it doesn't count in the second derivative. So we'll call this f double prime partition. So -2.5 is no longer part of it. However, I can use it for a test number because it is between these two numbers. Oh, I don't want to erase that. I need that. What was that? Decreasing? Yeah, that was decreasing and this was increasing. All right. I should probably buy another whiteboard and just have it off screen to hold all this information. All right, so let's go ahead and do this. We're going to test a number that's greater than 3. So we'll test 4. We're going to test -2.5. I shouldn't really cross it out. It's still part of the equation. It's just not a partition number anymore because this is now the second derivative. All right, and then -9 over here. And I'm going to spare you all the details and maybe say DIY it. Take your calculator, all right? If you're watching this at home, you can pause the video now. Take your calculator, plug in -9 here, and unfortunately, you also have to plug it in the denominator. Oh, sorry. That's not the one we're testing. Oh no, did I erase it? See what I mean? If I erase it, I'll lose it. What was it? It was that giant number. Oh, God. Please tell me you have it written down somewhere. I don't have it written down anywhere. It was that big giant number, 600 and something. What was it? 6, 7? I don't know. I'm not even going to guess. I'm going to say A, x squared, bx plus c. I forgot what A, B, and C were. They were those big numbers. You see what happens when I erase stuff? I erased it. I didn't write it down on a side note, and I lost it. It doesn't matter anyway what they are. They're just big, giant numbers. They were all positive. When you plug -9 in, all right, trust me, you're going to get a positive number. Just trust me at this point in the game. Now plug -2.5 in. Plug it into this whole second derivative here. Top and bottom. Yeah, you got to do the bottom too. You're going to get a negative number. And then plug in 4 over here, again, into all of these x's, and you will get a positive number. And I don't care what number you get. You just get some positive number. So that means that this is concave down. So this is like this. It's a max, concave down. This is concave up. All right. Now, normally you would say it's a min, but because it's, or an inflection point or changing concavity, but because it's an asymptote, it doesn't count. It's just it's being partitioned by the asymptote. And then over here, you have concave up as well. So we're finally ready, after all of that suffering and calculating and etc., etc., we're ready to draw the graph. Are you ready? I'm ready. All right. That's what I want to hear. You're ready. I should probably write this down before I erase it. You see what happens last time. So we have CU -infinity to -8 union 3 to infinity. CD only in the middle, -8 to 3. And now we can erase all this stuff. And then inflection point is DNE. So there is no inflection point. All right. Oh, and we have a max at -2.5. All right. Now, if we need y values, if the one thing you should never erase is the original function, because you might need it at the end to find your y values for your graph. All righty, here we go. So first thing you should do is put down your partition numbers and remember which ones were asymptotes and which ones were critical values. All right, let's start with -8. So 1, 2, 3, 4, 5, 6, 7, -8. That's an asymptote. All right. Now on your answer, you're going to have to write x equals -8 for the asymptote. I mean, when you draw it, you just say -8, but it's x equals -8. The other one is at 3. So 1, 2, 3. And again, you're going to have to type x equals 3. That's your other asymptote. All right. Critical value, -2.5. So right about here. -2.5. We're going to plug it in to here. Kind of wish I just would have done it a long time ago. So let's see what happens. So we got 2.5 squared. That's 6.25 times 2. That's 12.5. Let's just write this down, 12.5. And then I got 10 times negative 2.5. So that's negative 25. 2.5 times 10. I feel silly even doing that on a calculator. Negative 25. And then plus 14. All right, so that's the top. So all of this comes out to 1.5. Over, I don't know, I got to do the bottom now. Let's see, 2.5, negative 2.5 squared is 6.25 again. 5 times 2.5, or negative 2.5 is negative 12.5, and then minus 24. So do those first. It gives me a negative 36.5 and then add 6.25. So the bottom is negative 30.25. So I've got 1.5 divided by 30.25, negative 30.25. So this is negative 0.049. Which is negative 0.05. It's basically 0. So I'm going to draw the dot right there. It's so close to the axis. On the screen, on the computer screen, you wouldn't be able to tell. So I've got y max is essentially 0 at x equals negative 2.5. If you're rounding to the nearest tenth, that actually is 0. But I would accept negative 0.05 as well, okay? All right, and then we have concave down, right? So we know it's concave down. Where's that? Right here. So between negative 8 and 3, we know this is concave down. That's pretty easy. It's like an upside down parabola. Yeah. We have no inflection points, so it's not changing its concavity. And here comes the grand finale. Increasing, yeah. So notice this arrow, I'm blocking the arrow with my head, but this is actually going up like this. So it's increasing until it gets to here, see? You can see that, negative 2.5. And then it's decreasing, yeah. So this is decreasing like that. And then over here, off to the side, you can hardly see it. It's increasing. It's going up. That's this over here. From negative infinity to negative 8, that graph is going up. So I like to draw these little extra arrows to show sort of the flow. And then one last little touch. I don't think I have any more points to plot. No, I got the asymptotes, got the max. One last thing is what happens here is called the horizontal asymptote. And this goes all the way back to chapter 1. Take the limit of f of x, limit as x goes to infinity of f of x. And I'm going to say DIY. This is a review question. Chapter 1. The limit as x goes to infinity of this function is 2. So the horizontal asymptote horizontal y equals 2. So one last touch, we're going to put a dotted line passing through y equals 2. And that, my friends, was a lot of work. But I don't know, was it better than doing word problems? Because that's what we're doing next time. So that's the end of this example. Until we meet again, thanks for hanging in with me. I'm Dr. Jordan, and I'll see you on the internet.